Hello physics students. Remember in our last physics class, we began our journey into the beautiful ideas of calculus. Remember in class also that I said calculus consisted of two big ideas. One is called the derivative, and the second is called integration. We're going to be learning about both of these ideas in this topic, but first we're going to be focusing on the derivative for about 2 weeks. Now remember in class I said that I wanted to emphasize two things about the derivative itself. One is, what is a derivative? That's very important. A lot of people skip over that or forget about that when they move on to all the part 2 of that topic of derivatives, the techniques of finding the derivatives of various functions. But what is a derivative? Important to keep in mind and keep that rooted at the base of all your problem solving. Now remember, derivative had something to do with velocity and acceleration. Now remember, this is the equation that we learned for velocity when it came to just strict kinematics. Velocity was a change in displacement, or the x-coordinate as a function, or divided by a change in time. For example, you could go 100 meters in 20 seconds, and then your velocity over here would be 5 meters per second. But at any one instant, you could possibly be speeding up at a faster or slower rate. So in that 5-second journey, at the 1 second mark, maybe you're going a different speed other than 5, faster or slower. So what we do is we define what's an instantaneous speed. This is the big idea of calculus, is that we allow this delta t to shrink to 0, and we see how far something moves in that very small time fragment. For example, maybe you photograph the position of a car, the front of it, and 1/1000th of a second later, you photograph it again. And you find that that motion in that 1/1000th of a second, the car went a delta x of 2/1000ths of a meter divided by 1/1000th of a meter gives us 2 meters per second at that tiny fragment of time. We say at that instant, we say that instantaneous velocity. So that's the basic idea of what a derivative is. We allow this time to go very small, and we see how much this changes as time changes. So we need a new notation. We can't use the capital delta symbol from the Greek alphabet. So we say that a derivative is dx dt, the change in x per tiny change in time. And so that's how rapidly the x-coordinate is changing. That's the velocity of the object. Then velocity itself can change. So then we can find the derivative, the change in velocity for tiny fragments of time, and that is the instantaneous acceleration. But a derivative does not just pertain to physics, as I mentioned in our last class. It applies to economics, it applies to a lot of different things, and there's other kinds of derivatives. Let me just show you a couple examples. So, one is maybe you have an investment portfolio and it has a certain balance in it, okay? So you can take the derivative of the balance with respect to time. And maybe you find that the derivative of your portfolio balance is $1 cent per second, meaning every minute you make 60 cents, every hour you make 3,600 seconds, which is $36, and then every day times 24, so on and so forth. Now, of course, that rate can change itself, but that's the idea of a derivative applied to some economic application. But you could also have derivatives with respect to some other variable than time. Like, for example, maybe we have the derivative of temperature with respect to the x-coordinate. What that means is maybe when you're moving in the positive x direction 1 meter, you find that the temperature drops by 1 degree Celsius. Now, it could change with respect to time, like when the wood stove burns out, it gets colder and colder. Maybe we have negative degrees Celsius per second. But we could also step in this direction and see if that variable changes with respect to x. Maybe because we have a wood stove here and we're stepping away from it, so we're dropping in temperature as we move in X degrees Celsius per meter. So the derivative, what it is how rapidly something is changing as another variable is itself changing. In our case, we're going to be sticking with time. As time changes, how does X change? As time changes, how does the velocity change? That's velocity and acceleration. So that's what the derivative is. Then I said there are techniques to finding the derivative. We learned in class a basic technique for a power function. Like, for example, if our function was t to the negative third power, to take the derivative of that, what you do is you move this negative 3 in front, and then you subtract 1 from the exponent, and that's the rule that we learned for simple power functions. But again, as I said, there are so many functions: sine, cosine, exponential, natural log, on and on. So we have this basic technique. We need more techniques for more different kinds of functions. What are those rules? Today we're going to learn another technique for functions that are a little bit more complicated than these. For example, what if we had, what if instead of t, no, lighting is bad here. Let me take a step back. Hopefully you could see this. What if instead of having t to the negative third like we had all of this function to the negative third power? More complicated than this, but it looks kind of like this. So what's the rule for taking the derivative of such a function like that? That's the topic for today, and it's called the chain rule. So let's begin. Derivatives and the chain rule. Here's the rule. It may look intimidating. You probably don't know what this means, but we're going to jot it down. If you take the derivative of function x with respect to time, you could also take the derivative of x with respect to some different variable u. It's still equal as long as you multiply this derivative by the derivative of that u function with respect to time. You could almost think of it as these du's canceling, giving you that. All right, well, what does that mean? How does that work with a real function? So let's take a look at an example. Here we have an example. If x equals 2/3 of 4t squared plus 2 to the negative third, determine the velocity. Now I put this in a different color to hopefully help you see the pattern. Because what we do is we take the derivative of this function as if this was just a regular old variable. And we know how to do that. We use the power rule. We move the negative 3 to the front and then we subtract 1 to make this to the negative 4. So let's go ahead and do that. But remember, I said when we studied physics, math is no different than English class. When you write a paper, yes, you need an introduction sentence, you need a conclusion, you need punctuation. So there's a certain way to show these solutions, a nice, elegant way. So I'm also demonstrating that. We begin by writing. If we want the velocity, we start with the general rule of what velocity is: derivative of x with respect to time. Then we substitute our entire x function into that expression. So where this x is, we put everything there. So here's what we do. Like I said, we pretend we just have the regular power function. We move the negative 3 to the front, and then we subtract 1 from the exponent. But we're not done yet, because we just took the derivative of x with this entire mess over here as if it were its own variable. Now we need to multiply by the derivative of that variable with respect to time. So see this function, that's my u. I have to multiply by the derivative of that, and only then do I find the derivative, which is the velocity. So now we can proceed and continue on. So I'm going to take the derivative of this. You should look at this and say, oh yeah, I know how to do that and feel comfortable with that. This is just a polynomial here with the power rules. So we look at this 4t squared and we multiply 2 times 4, giving us 8, and subtract 1 to the exponent. We have a 1 here. Plus the derivative of 2, well, 2 never changes. So derivative, I could put a plus 0 here if I want. You know what? Maybe I will, just to hopefully make it clearer. But you should feel comfortable with this by now. And then finally, I'm just going to touch this up by bringing the at to the front, negative 16t, and there's my function. So there's my derivative, there's my velocity. So if you haven't already copied this down, let's take a moment, pause, and copy these notes into your notebook. All right, so actually that's it for the new techniques for today. But we still have some more that I want to show you. because there are other things about derivatives that are very useful. One thing we're going to learn about today is that one application of derivatives, in addition to finding velocity and acceleration, it could also help you find the maximum of a function, the peak, or the minimum of a function, the bottom. When a function goes like this, what is that point on the maximum? How about down here? What is that point down here? So that's the next topic we're going to learn about today. So give me a moment and I'll put some new notes on the board here. Okay, so here we have it. Derivatives and maximums and minimums. I just realized when I was writing this down, is the plural of maximums maxima? I don't know. Anyway, if it is, then I'm sorry, I have a grammatical error. But anyway, let's suppose we have some function and I graph it and I see that it has this particular shape. Here's the peak, what we call a maximum, a local maximum, because here we get to other, but in this region it is the maximum. Here's a local minimum in there, like the bottom. So how can we use derivatives to find those points? Well, if you look, remember, derivative is how fast something is changing with respect to another variable. Said graphically, what a derivative is, it's the slope of a graph. And what can we say about both these points regarding to slope? The slope is 0 at both the maximum and the minimum. So let's jot that down. All right, so there we are. So far, calculus-wise, it looks like there's no difference between these 2 points. But we could see there's clearly a difference. One is going like this and one is going like that. There's another calculus idea that will allow us to distinguish between these two. Derivative is slope. And if you think about the slope here is positive. The slope, right, this graph is sloping up like this. The slope here, as we said, is 0. And the slope here, when a function goes down like that, it's negative. And here we have a negative slope coming into this point. Then we go to a 0 slope. And then we go to a positive slope. Now, let me ask you what kind of change it is when something goes from a positive value to a 0 value and then to a negative value. Positive to 0 to negative is a negative change the whole time. And so the slope itself is changing by a negative amount. And the slope itself is a derivative. So we're saying, how much is the derivative changing by again? In other words, we're taking the derivative of the derivative itself. And so we write that mathematically like this. And as we saw, the change is always negative less than 0. And what that means from a picture is when the second derivative is less than 0, we could see graphically, that means the function there is concave down. Right? Concave is not when something's flat. It's like this, concave. And this is concave down, okay? Over here, on the other hand, what's the change when something goes negative to 0 to positive? In other words, from negative up to 0, then up to positive. What kind of change is that? That's a positive change. And slope is changing by a positive amount. Well, slope is a derivative. And so we're saying the change of a derivative, in other words, a derivative of a derivative, which is the second derivative. We write it like this. In this case, it's negative to 0, it's greater than 0. And that means from a graph, when you have a second derivative that's positive, greater than 0, it means the function is not concave down, but concave up. Well, if you haven't had a chance yet, then go ahead and copy these notes into your notebook now. What I'm going to do now is an example using these ideas. So let me make some room and jot down a few more notes. Okay, here's the example. An object's x-coordinate is given by this function, this polynomial. Determine x max and x min. Well, one crude way would be to just go on the graph here and say, okay, the maximum looks like, I don't know, 7 or 8, right? But that's not very precise. And maybe it's at 1 second, but maybe it's at 1.1. We're not sure, but it's close to there. And the minimum is down here where the slope is 0 also. And so we can estimate maybe it's 4 seconds and maybe like, 2 or something like that. But again, too crude. So now we're going to use calculus, the principles we learned over here, to figure out and analyze this and figure out those exact values. By the way, if you haven't already copied this down, let's take a moment to catch up so you're not rushing. So go ahead and take a moment to copy these notes down. All right, so once again, the big idea, the x max. Well, I guess maybe I'll say x max and x min. At both those locations, the thing that's true is the derivative, change in x with respect to time, the slope of that function is 0. And so what I'm going to do is, this is the general expression. We always start with that. Now we're going to plug in our specific expression in this case, which is our x function. Now, if I was in class, I would stop and say, does anyone here know how to take that? And we'd see with a show of hands who can do it. But maybe what I'll do, if I remember in YouTube, I'll create a little pause here for you to be able to sit back and think just for a couple seconds in your head, what is the derivative of this, to test yourself from what we learned last time. All right, so here's what you should do. You bring the 3 to the front with the 1/3, which gives us 1/3 times 3 times t to the 2 power. Then what you do is this 5/2 term stays here. The derivative of t squared is 2t to the 1 power. You don't even have to write to the 1 power. And then the derivative of 4t, well, the 4 part stays. And then we have t to the 0. I'm not going to write that. That's 1. And then we have the derivative of the number 5. Derivative of any number is always 0. So here's our derivative. Now we need to solve for time. Let me just rewrite this. 0 equals. Now normally, what we would have to do, if these were all decimals or something like that, we'd have to use the quadratic equation. The opposite of b plus or minus b, the radical b squared minus 4ac all over 2a. But I picked this example so it'll be nice and easy, so I didn't have to do that. This factors, we can say 0. Right? You could verify that if you want, just quickly expand that out. You see, you get this anyway. And then what we see is, when is this function 0? Well, one possibility is t equals 4 seconds, and we have 4 minus 4, 0 times something is 0. And the other possibility is t is 1 second, and we have 1 minus 1 here, 0 equals 0. So 1 is t. Well, let me leave a little space. Now, if we didn't have a graph, we would have to take a second derivative and plug these numbers in and see in which case was the second derivative positive. That would mean concave up, minimum. Which place was a negative, concave down, which would mean that was a maximum. But we don't have to do that because I provided you a graph. We already can see just from the graph that at the 1 second mark, that is a maximum. So this is the time of the max. And the 4 second over there, you could see that's like the minimum. And so we save a little time without having to go and take the second derivative if this were a problem without a graph. So it didn't ask for that. It didn't ask for when the maximum and minimum occurred. It asked what the actual maximum and minimum were. So now we need to plug these back into our original function to see what this peak and this little bottom part are. So let's do that now. By the way, if you're a little behind, let's take a moment, pause the video, and allow you to catch up with the notes. Okay, so the maximum value, which occurred at 1 second. And now what we would do is just go ahead and punch it on a calculator. I did it ahead of time, so let's just see what that result is. So there it is. Now remember on the graph I said, well, maybe it's 6, 7, or 8 or something, you know, some kind of like peak over there. We couldn't tell, but now we have the exact value. We also want the minimum, so what we have to do is plug in the time of the minimum 4 seconds into our original function. So let's go ahead and do that. So plugging in 4 seconds in for time. And then again, I did this already. I punch it on a calculator. That's what you would do. Punch it on a calculator and you get. All right, so if you need a moment, then let's pause, allow you to copy this down. All right, so that's our second day studying derivatives. Remember, it's the first of 2 big ideas in calculus. One is the derivative. We're going to spend 2 weeks on that. And then the second is integration. We're going to spend 2 weeks on that as well, about give or take. Within both of those, the important thing is to know exactly the concept behind it, what a derivative means. And what it means is it's how fast something is changing, the rate of change of something with respect to some other variable. In our cases, we're sticking with time, but that's not necessary for derivatives. We're finding dx, how rapidly x is changing as time goes on, as the clock runs. Is that positive? Then x is going in the positive direction. Is it negative? Then it's going, the object's moving backwards, and the numerical value is how fast it's moving, the velocity. V equals dx dt. And then we learned that the acceleration is how rapidly the velocity is changing with respect to time. In other words, it's the derivative of velocity with respect to time. So those are the 2 big concepts. The techniques, the second part of derivatives, we already learned the power rule last time, you know, in our last class, just using this simple rule of moving the exponent to the front and then subtracting 1 from the exponent. So we learned that last time. This time we learned the chain rule. What happens when we have a power function and within that power is a whole nother function? And so I erased it already, but if you don't remember that, go back in your notes and look how we took the derivative using the power rule for the larger function. Put the exponent in the front, subtract 1, but then we had to fix by multiplying by the derivative of that function inside the parentheses with respect to time. That's the chain rule. Over the next coming days, we're going to look at sine, cosine, exponential, natural log, all those functions. What are the rules for those? And additionally, we learned that the derivative tells us where a maximum or a minimum occur because the slope of the functions is 0 in both maximum and minimum. The second derivative tells us if it's negative, it's concave down. That's a maximum, a peak of a graph. When the second derivative is positive, the function's concave up. And that's like the bottom, the minimum of a function. So that's what we learned also. All right, I hope you found the video clear. I hope you learned a lot. I'll see you next time in the next physics class.